So good evening, students. So last class, we have completed 10 MCQs. Till here, I think I have completed. We'll go for the next one. Yes, we have to start from here. Okay, so this is a question. Which of the following biphenyls is optically active? Okay. So these are the four options. So which among the following are optically active? Yes. So we have studied about stereochemical aspects in haloalkanes and haloarenes. So based on that, this is a problem. What is optically active? What do you mean by optically active? Optically active means what? Yes. Which can rotate the direction of plane polarized light. Yes. So optically active are those compounds which can rotate the plane of polarized light. Okay. As well as they have a chiral centers, right? So these are stereoisomers which are optically active and they have a chiral center. So and they do not have a plane of symmetry. So optically active compounds are, they do not have a plane of symmetry. Okay. Now here, okay. So here you, so if you consider the first compound, okay, and what do you mean by plane of symmetry now? So now these two are ortho. I'll take the option B. Okay, option B, you can see that here these methyl groups, right? These are ortho substituted. Ortho substituted means what? From here, this is ortho substituted. Okay, this is at second position, right? So these are called as ortho substituted. So ortho substituted, and you can see that there is, if there were again here also methyl groups, right? There would be steric hindrance, right? What do you mean by steric hindrance? There would be crowd, right? There would be crowd. So this is what you mean. So these are ortho substituted in this. So what is there? So because of the steric hindrance, what will be there? There will be, they are perpendicular to each other, and due to perpendicular to each other, no planar to each other. These are no plane to reach each other. So is there any plane of symmetry? So remember what are optically active. Optically active means they have chiral center, okay, and there should be no plane of symmetry. Okay, no plane of symmetry. No plane of symmetry. Okay, now if I put here this, so is there a plane of symmetry? Yes. So there is a plane of symmetry. Plane of symmetry means what? If I put a mirror here, so this is equal to this. If I, so this half molecule will be equal to the other half molecule, right? So if I put a mirror here, so this half is equal to the other half. So is it a chiral center? No, it is not a chiral center, and it does not, it is having a plane of symmetry. So this molecule is not that. Okay. Then if we go for option number C, if I put a plane of symmetry, okay, what, so there is a plane of symmetry is present, right? So plane of symmetry is present here. So this half molecule will be equal to the other half, right? So there is also plane of symmetry here. Then in D, okay. Now here also, if you consider this particular compound here, what is this is ortho substituted, this is also ortho substituted. So if I put a plane of symmetry here, okay, so what will happen, this half will be equal to the other half, so there is plane of symmetry here also. Okay, so because of this, this is also not correct. Okay, so D option you can see, so D options you can see these all atoms are crowded. Okay, these are all ortho substituted, and because of this atoms, presence of atoms, so these are, there is a steric hindrance. Steric hindrance means what? Steric hindrance means there is a crowd. Okay, there is crowd. So these are not these are perpendicular to each other, and they will not be in the plane. Okay, they will be not there in the plane with each other, so therefore they are optically active. So if they are not in plane, so if they have a plane of symmetry, means they are optically inactive. Now here these are they are not having plane. Okay, these are perpendicular to each other. When they are perpendicular to each other, there will be no plane with each other, and therefore they are optically active. So D is the option. So whenever you want to see any particular compound, if it is optically active, you want to check, you have to see for a chiral center, and there should be no plane of symmetry. Okay, in all the other three, you can see there is a plane of symmetry. If plane of symmetry is there, so one half of the molecule is equal to the other half. Now here what is happening, these all atoms, okay, these all molecules, they are what, they are perpendicular to each other. So if they are perpendicular to each other, what will happen, they will be not in the plane. Okay, they are not in the plane, and therefore they are optically active. So D is the correct answer. Understood? So what is the reason for optically active? They are they should have a chiral center, they should have no plane of symmetry. Okay, so here as the four atoms, they are having what, they are ortho substituted. As they are ortho substituted to each other, there is steric hindrance. Steric hindrance means there is crowd, right? There is crowd towards each other, so they are perpendicular to each other. So they are perpendicular to each other. Okay, so option D is the right answer. So we'll go for the next one. So for the following reactions, okay, which of the following is the correct? So there are three reactions given. So you have to see out of the following okay, statements, which one of among the one is the correct one. Okay. Try. So try solving the question. So the first equation, our first equation is what? First equation is CH3, CH2, CH2Br plus KOH. Okay, giving you CH3, CH double bond CH2 plus KBr plus H2O. So what is happening here? Yes, what is happening here? So this is what? So this is KOH is a base, right? KOH is a base. So base is acting here. So base is present, right? So base, what will happen? It is called as a base, or OH is a nucleophile because it has a lone pair of electron. So what will happen here? And this is what? This is a alkyl bromide, right? This is alkyl bromide. So this is alpha carbon, this is beta carbon. So what you can see in the product, what is happening from the alpha beta region? Okay, so there is a formation of double bond, and this K will be combined with Br. Okay, and there is a substitution reaction, right? So here there is elimination of what? There is an elimination of HBr minus HBr. Okay, so this is, and from a alpha beta carbon, from the beta carbon, there is a, you can see from the reactant and product, right? So this is CH2, this is CH. So from a beta carbon, so there is elimination of hydrogen. So this is a elimination reaction. So the first reaction is what? It is a elimination reaction, or it is called as beta dehydrohalogenation. Okay, dehydrohalogenation. Okay, so because minus HBr, right? Minus HBr, so it undergoes a elimination and the beta hydrohalogenation, dehydrohalogenation reaction. So this is our first reaction. Now we'll see the second reaction. Okay, so the second B option, we'll see B reaction, CH3, okay, Br, CH3 plus KOH, giving you CH3, C, CH3, HKBr. Okay, so what is happening here? What you can see here? OH, right? So this is acting as a what? OH is there. So OH is what? It is a nucleophile. Okay, OH is a nucleophile. So what is happening? This will attack. Where it will attack? So this will attack at this particular carbon and this Br will leave. Okay, so it is undergoing a what type of reaction? It is a nucleophile. So KOH here, OH is acting as a nucleophile and it is undergoing a substitution reaction. Your Br is being replaced by OH. So this is what? Nucleophilic substitution reaction. It is what? Nucleophilic substitution reaction. So this is an example for substitution reaction. So we'll go for the next one. C. Now here, what type of reaction it is? Br. Okay, so Br2. So it will undergo a heterolytic cleavage and this will be plus, this will be minus. So what will happen? So this is a nucleophile. So whenever you have a double bond, so this is acting as a nucleophile, right? So your benzene, cyclobenzene, it is acting as what? It is acting as a nucleophile. So now what is happening here? The Br plus. Okay, so Br plus will attack first. So it will attack what type of? So it will be it will attack this. So it will be electrophilic. So what type of addition? So across the double bond, first there will be addition of one Br. Okay, so it will first. So how it will be? I'll just show stepwise. So this Br, it will cleave as Br plus and Br minus. Okay, so that is delta plus delta minus. So there will be formation of, so this bond will break here and your Br will be added and here it will be positive. Now next addition, another Br which is left, it will add up across this positive charge. So this is what? It is a electrophile, right? So attack of a electrophilic addition reaction. So at a electrophilic, so this is electron deficient, right? As it is electron deficient, so what is happening? You are adding, right? So addition of bromine is taking place at the nucleophile. So this is a example for electrophilic addition reaction. So this is a electrophilic addition reaction. So which is the correct answer now? First one is elimination reaction. Second one is nucleophilic substitution reaction. And the third one is addition reaction. So which is the correct answer? See the options A, B, C, D. Which among the following you feel is correct? Yes? It is D. Yeah, right. So it is D. Okay. So like this. So like this, you are going to solve the equation, that is the reaction, and then you have to conclude which among the following statement is correct. Okay, understood? So we'll go for the next one. Two possible stereoisomers of CH3, CHOH, COOH is, okay. So which are optically active are called as what? So what are they called as? First is atropy isomers, atrop isomers. Second one is B option enantiomers, C is mesomers, D is diastereomers. So this was a question asked in 2015. So the compound is CH3, CH, okay, CH3, CH, OH, COOH. So this can be written as So how this can be written? So I can write this as one form. I can write this as this DNL form. Okay, CH3 COH. Okay, so with a mirror image will be CH3 CHOH COOH, right? So these are the two forms, two possible structures. Another, so you can see that the two, these are structures. Okay, so these two stereoisomers, they are mirror images of each other. And if you place one on other, are they, what you say, are they superimposable on each other? What are these called then? So these are mirror images. Okay. In this case, you can see the two structures when I have drawn them. Are they superimposable on each other? Suppose, see, these this is one structure. Okay. Now what I'll do, I'll place another structure here. So this is the mirror image of each other, right? Our hand, right? They are, now if I put one mirror on the other, one component on other, are they superimposable? No. Then when one stereoisomer is not superimposable on other, then it is called as what? They're called as what? They're called as enantiomers, right? What do you mean by enantiomers? Enantiomers are stereoisomers which are non-superimposable mirror images. So these are the non-superimposable mirror images are called as enantiomers. Okay. So the two possible structures, okay, which are optically active. Optically active means they have a chiral center and they do not have a plane of symmetry. So but they are non-superimposable. So when you take out their mirror image and you put one above the other, they are non-superimposable. So they are called as, such compounds are called as enantiomers. So option B is the right answer. Understood? Okay, so option B is the right answer. Next one, which of the following acid does not exhibit optical isomerism? A, malic acid, B, alpha amino acid, C, lactic acid, D, tartaric acid. Yes. Which of the following acid does not exhibit? Does not exhibit means what? They will not show. They means they are optically inactive. Okay. Optically inactive means they should have no chiral center. There should be absence of chiral center and there will be plane of symmetry. Now malic acid. What is the structure of malic acid? COOH. Okay, I'll write it like this. So I'll take the first option. A, HO, double bond O. Tell me whether it is having a chiral center and plane of symmetry. No, right? So they don't have, so there is a absence of chiral center, absence of chiral center. So they are optically inactive. So they are optically inactive. Okay, they are optically inactive. So now we'll see the next one. We'll see other options also. Okay. Next is alpha amino acids. How do we write alpha amino acid? Alpha amino acid C. Okay. Then here R group, H. Then one carboxylic group will be present and one amino group. Okay. So is it a chiral center? Is there a chiral center in this? Yes, there is a. So this compound is optically active. Why it is optically active? Because of chiral center. Okay, because of presence of chiral center. So this is a optically active. Okay. and they don't have a plane of symmetry. And here you can see there is a plane of symmetry. If I put a plane here, so this half molecule will be what? It will be equal to the other half, right? So there is no chiral center as well as there is plane of symmetry. In this, you have a no plane of symmetry, but they have a chiral center. Okay, so this is option C. Now we'll see option C now. Option C is lactic acid. What is the structure of lactic acid? C, COH, then OH. Okay. What is this? Is this carbon a chiral center? Yes. So this is also having a chiral. Okay. Chiral center. So this is also optically active. Okay. So now we'll go for the next one. D. D compound is what? Tartaric acid. Tartaric acid, what is the structure? HO. Now tell me, for this compound, is there any chiral center? So this one is chiral center, one chiral center, and another is this chiral center, right? Okay, so there are chiral, two centers are present. So this is also optically active. So which is the correct answer now? They have asked which of the following acid does not exhibit optical isomerism, means which are not optically active. Which is the answer? Yes. Others? Yes, it is A. Understood? So whenever you are checking for optically active, you have to see whether if it is optically active means they should have a chiral center. Okay, it should have a chiral center and there should be no plane of symmetry. Yes, A is the answer. Okay. I hope this is clear. We'll go for the next one. Chiral center means what? For that carbon, 4 different groups will be attached. 4 different group atoms will be attached. Okay. We'll go for the next one. So consider the reactions. So these are the 2 reactions. So you have to tell the mechanism of this reaction. 1 and 2 are respectively. Okay. So these are the 4 options. So can you tell me? Try solving this. CH3 twice, CH, CH2Br. Okay. C2H5OH. So there are 2 reactions. You have to tell whether it is undergoing SN1 reaction or SN2 reaction. Okay. Yes. Others? Komal is saying C. What about others? Okay. So you are seeing Komal and Netravati are saying C. So we'll let's check what is the correct answer. Okay. So CH3, CH2, CH2Br. Okay, CH3 twice it is. Now, first we'll see what is SN1 reaction. So for some students who have not joined the synopsis, okay, we'll see what is SN1 and SN2. What is SN1? What do you mean by SN1? SN1 means it is unimolecular reaction. It is substitution nucleophilic unimolecular reaction. Okay. How does the reaction follows? There is a alkyl halide. Okay, alkyl halide. What is happening? Alkyl halide. So there are 2 steps involved. The first step, there is a what heterolytic cleavage, breaking of the bond takes place with the alkyl halide, and there is a formation of carbocation Okay, there is a formation of carbocation, and later in the second step, what happens? The nucleophile attack will take place at the carbocation, and you get a product. Okay, you get a substituted product. Here, what you yield is racemization. Okay, you yield racemization mixture. That is, you get both inversion as well as retention of configuration. Okay, the products obtained are racemic in nature. That is, you get inversion as well as retention. Here, the stability of the carbocation, so here the reaction, it depends upon the stability of carbocation. That is, what is the stability of carbocation? That is, tertiary is more stable than secondary and then the primary. So this is about SN1 reaction in short. What do you mean by SN2 reaction? SN2 reaction, it is a bimolecular reaction. Okay, so the rate of the reaction depends upon the concentration of the substrate as well as nucleophile. In SN1 reaction, it depends only on the concentration of substrate. Okay, so here in SN2 reaction, what happens? So there is alkyl halide. So the nucleophile will attack the alkyl halide from behind, okay, from the back side, and it will go via a one step, that is nucleophile attack with the alkyl halide. Okay, and breaking and making of the bond takes at the same time via a transition state. Okay, it does not undergo the formation of carbocation. It will go via a transition state, and what will happen then? The nucleophile will your leaving group will leave, and you will get a product. So this is complete inversion. So here the product yield is complete inversion. Okay, how is the reactivity here? So here the primary are more stable than secondary is more stable than tertiary. So methyl cation is also most stable and tertiary is the least stable when you're talking about SN2 mechanism. So this is some short briefing about the SN1 and SN2 mechanism. Now we'll see the reactions. So if I consider the first reaction, that is CH3 twice CH, CH2Br. Okay. Now first is what? So there is a base. Okay. So base is there, OH. So what will happen? First, what will happen? First, the nucleophile, whether it is SN1 or SN2, what will happen? The nucleophile will leave. The leaving group will leave. So this is a leaving group. Then what will form? So it will form CH3 twice. Okay, CH2 plus. Now CH2 plus, here the carbocation formed is attached to only one carbon. So this is a primary carbocation. So primary carbocation is most stable in what form? It is most stable in SN2 mechanism, right? So primary carbocation, thus this is a SN2 mechanism. So what will happen? CH3 twice, CH, CH2, and this O C2H5 will form, okay, plus HBr. So this is the product. So this is a SN2 mechanism. Okay, this is a SN2 mechanism. Why? Because you can see the carbocation formed is primary in nature because the carbon is attached only for one carbon. Now we'll see the second reaction. Okay, second reaction. What is second reaction? CH3 twice, CH, CH2Br. Okay, in the presence of C2H5O minus gives you what? Now here again, what will happen? The first, what will the leaving group will leave? So you will be CH3 twice, CH, CH2 plus. Again, here the carbocation formed is primary in nature. Okay, and thus this is also a SN2 mechanism. So which is the correct answer? So CH3, CH, CH2, then O C2H5. Okay, so what is the correct answer? It is C. Yes. So who all had said C? So Komal and Netravati both had said C. Okay, so C is the correct answer. Understood? So like this, you have to solve it. Okay, you have to see the stability. You have to see the stability of carbocation. So stability of carbocation, it plays a very important role. Okay. So you know that in SN1 reaction, tertiary are more stable than primary, secondary, and then primary, and then methyl cation. While in SN2 mechanism, methyl carbocation is more stable, then primary, then secondary, then tertiary. Okay, so we'll go for the next question. Which of the following compounds undergoes nucleophilic substitution reaction most easily? Okay, now here, first of all, we'll see that For nucleophilic substitution reactions to occur more easily, there should be presence of what type of group? There should be presence of electron withdrawing groups. So whenever electron withdrawing groups are attached to the benzene, okay, then what will happen? Nucleophilic substitution reaction, the rate of the reaction will be increased. So whichever, so in the among the four compounds, you have to see that if electron withdrawing groups are attached, okay, then to the benzene ring, then what will happen? The nucleophilic substitution reaction, the rate of the reaction will be increased. Now here, the electron withdrawing groups such as nitro group, okay. So this is a nitro group, okay. Suppose this is a nitro group now. Okay, so this is a nitro group. Now here, what will, so whenever the nitro group is present, that is nitro group is an electron withdrawing group. So electron withdrawing group, whenever it is present to the benzene ring. So as you see among the nitrogen and oxygen atom, okay, the oxygen is most electronegative than your nitrogen. So what it will do, it will tend to pull the electron towards itself. So as a result, what will happen? This nitrogen will be electron deficient. So the electrons from the double bond will be pulled towards the oxygen. Oxygen, as it is highly electronegative, okay, the electronegativity is more. So electron from the double bond, so oxygen, it will attract, okay. And what will happen? This nitrogen which is present, so this nitrogen will become electron deficient. Thus, what it will do, it will tend to pull the electron density from the benzene. So nitrogen will become electron deficient. Thus, it accepts the electron density from the ring. Understood? So as oxygen is highly electronegative atom, then the nitrogen, it will pull the electron density from the double bond towards itself. So as a result, this nitrogen becomes electron deficient. So it pulls the electron density from the ring. So so there is a presence of what? It becomes minus R effect. Minus R effect means it is due to resonance effect. It is due to minus resonance effect. Okay. So due to minus, therefore, due to minus resonance effect, it will create the deficiency of the electron density in the benzene. So it will create the electron deficiency in the benzene ring at ortho and para position. As the nitrogen, it is electron deficient, it will pull the electron density towards itself. So as a result, at ortho and para position, there will be what the electron density will be the deficiency in the electron density because of the presence of electron withdrawing group. So whenever electron withdrawing groups like nitro are present on the benzene ring, it withdraws what? It withdraws the electron density from the benzene ring due to minus R effect. Okay. So why? Thus it creates the electron deficiency of electrons on ortho and para position. So among the following, now we'll see. So if I consider this particular C option, okay, so Cl is present. So Cl will show what? Cl will show plus R effect. So it shows plus R effect, and it will show minus I effect. That is inductive effect minus I effect. Okay, and OCH3, it shows plus R effect. It shows plus R effect. Then if I consider now this option, that is Cl D option. So because of the presence of Cl, it will show minus I effect. Okay, minus I effect. Then when you are considering this option, what is that? Cl and NO2. Okay, whenever when you are considering this particular option, that is Cl and minus 2, that is Cl will show plus R effect and minus R effect, and nitro group will show what? R, minus R and minus I effect, right? And here this will show plus R effect. So this is so because of the nitro group, so which is the correct answer? It is A. So A is the correct answer. So because of the presence of electron withdrawing group, what it will do? It will pull the electron density. So the nitro group, the nitrogen will be electron deficient, thus it will pull the electron density from the nitrogen. Okay, so because in the electron density is pulled from the nitrogen, so there will be deficiency. So deficiency will be created at ortho and para position. Okay, so due to minus R effect. So it is A. So so which among the following compounds undergoes nucleophilic substitution reaction most easily is whenever you have a electron withdrawing groups. So electron withdrawing groups such as nitro group, they tend to increase the rate of reaction when okay, that is nucleophilic substitution reaction rate is increased because of the presence of nitro group. Remember this. Okay, so we'll go for the so it is A option. Okay, A is the correct option. So just see, so this is the A. A is the answer because you can see in the among the other options. So this is the nitro group is the electron withdrawing group. Okay, so we have seen the other groups. What are the so this, okay, how, so it shows plus R effect, minus I effect, right? So nitro group, because of the presence of nitro group, it will show, it will readily show increase in the rate for nucleophilic substitution reaction. Okay, so we'll go for the next one. Which one of the which one is most reactive towards SN1 reaction? Okay, this you can tell me which among the following. SN1 reaction means what? SN1, for SN1 reaction, most stable is what? Formation of carbocation, right? So more, so the stability tertiary will be more stable than secondary, then primary and methyl carbocation. So for SN1 reaction, so consider the 4 reaction and see which among the following will show the highest stability of carbocation. So the alkyl or the aryl halide, the stability of the carbocation, it will increase in what order you have to see. Okay, Komal is saying C. What about others? Priyanka is also saying C. C6H5. Okay, C6H5, C, H, C6H5, Br. So this is the first compound. Second compound is C6H5, CH, CH3, Br. Then the third compound is C6H5, C, CH3, then C6H5 and Br. And the fourth compound is C6H5, CH2Br. Okay, so if this breaks, there will be formation of primary carbocation. Okay, this will be formation of primary carbocation, right? So because it is attached to only this, then if this breaks, if here what it forms a tertiary carbocation because this is further attached to 3 more carbons. If this breaks, there will be secondary carbocations, and if this break, this also gives rise to secondary carbocation. So option, yes, C is the right answer. Good. Okay, so Netravati, Priyanka and Komal have answered it right. It is C option. Okay, so C is the correct answer. So we'll go for the next one. Understood, you have to check for the stability. Okay, always you have to check for the stability. If it is SN1, tertiary will be more stable and least will be methyl carbocation. And if it is SN2, primary will be more stable and sorry, methyl cation will be more stable, then primary, then secondary, and then tertiary. Okay, you have to follow this order. So we'll go for the next question. So the next question is the correct order of increasing reactivity of. So these are the 4 compounds. CX bond towards, you have to tell the reactivity of CX bond towards nucleophile in the following compounds. Okay, so just see which is the correct. So you have to tell the order of the increasing reactivity of CX bond. Okay, nucleophilic reactivity first will go from the behind. Option A. Okay. Komal is saying option A. What about others? Yes. Okay. Just see here now. What is the CX bond towards nucleophile in the following reaction? Now, if this bond breaks, okay, so this will be carbocation formation. If this bond breaks, so here, now when you're talking first aliphatic, so whenever reactivity you're checking of aliphatic reactivity will be more as compared to that of aromatic. So first we'll see third and fourth, okay. Third and fourth. Third is what? CH3C, CH3, CH3X. Right, so this is tertiary. Then here it is CH3C, CH3HX. So this is more stable, right? Third is more stable first, and then come your fourth. That so third is more stable. Then your fourth is more stable. Then amongst the aromatic ring, okay, amongst the aromatic ring, you have to see for electron withdrawing group. You know, for nucleophilic substitution reaction, if there is presence of electron withdrawing group, then what will happen? There will be electron withdrawing group. Then the reactivity rate will increase towards the nucleophilic substitution reaction. So then it will be second. So second, right? And then comes the first. So first, so you can check the options. So first is more stable, then second, then fourth, and then third. So option A. Okay, option A is the correct answer. Yes. Did you understand others? Okay, so whenever you are talking, so these are two sets are given of aryl halides and two sets are of alkyl halides. So whenever you are talking about reactivity towards the nucleophile, aliphatic compounds will be highly reactive than the aromatic, okay, aryl halides. Alkyl halides are highly reactive. So you have to check for the reactivity first. Now here, when you're seeing here, so there are three alkyl groups. Three alkyl groups means, right, three alkyl groups. So this is more stable. Then there are two alkyl groups. So this is more stable. So among this, and here when you're talking about alkyl bonds, we have just seen that whenever electron withdrawing groups are present, so the rate of reaction will be increased for towards the nucleophilic substitution reaction. So nitro groups are present. So this is the second one. So first comes the third, then fourth, then second and first. So it is order is A. So A will be less, 1 will be less than 2, 2 is less than 4, and fourth is less than third. So third is the most stable. So this is the increasing order of their reactivity. Okay. So the next question, in the following reaction, so this is a reaction that is C6H5CH2Br giving you Mg ether H3O plus giving you what? Okay. So just see, this is a Grignard reaction, right? So last class or before that class, somebody had asked me to explain about Grignard reaction. So Grignard reaction is what? RMGX. So RMGX is called as Grignard reagent. Okay. So Grignard reagent, or they are called as organometallic compounds. So they form what? They form organometallic compounds. So question is asked, what is Grignard reagent? What is the formula? So Grignard reagents are organometallic compounds or organometallic halides. Okay, and the formula is RMGX. So the reaction, we'll see this reaction, then you'll come to know. Okay, so C6H5CH2Br in the presence of Mg in ether, okay, and it undergoes further hydrolysis. So what it will form? First C6H5CH2Br, okay. What will happen in this reaction? CH2Br. Okay. So this in the presence, first step we'll see Mg and ether. Mg and ether, what it will form? It will form C6. So I'll write it like this. Okay, then you will get to know properly. So if I write like this, you will come to know easily. So C6H5 is your aryl group. So Br in the presence of Mg and ether, what it will form? It will form what? CH2. Okay, Mg will attack, so it will form CH2 MgBr. Okay, so this is an organometallic compound. So this will undergo further hydrolysis. Okay, hydrolysis, what will happen in hydrolysis? So H plus and OH minus will, hydrolysis, it will split into H plus and OH minus. Okay, so H will attack here. Okay, H will be added here and OH will be added here. Okay, so this will be CH3 plus MgBrOH. So what is the option? Option C. Understood? Okay. So option C is the product. This is the product X which is formed. So that is toluene. So the product formed is what? It is named as toluene. Okay. It is named as what? It is named as toluene. Understood? Yes. Is it clear? Is it clear? Yes. Okay. So we'll go for the next one. What are the, oh, yes. Which of the following reaction is an example of nucleophilic substitution reaction? Now I want the answer from you all. Which of the following reaction is an example of nucleophilic substitution reaction? What is nucleophilic substitution reaction? There is a alkyl halide, there is a nucleophile. So this nucleophile will attack the what? It will attack the substrate. Okay, and in case there will be leaving group. Okay, so attack of the nucleophile at the carbon substrate. Okay, and thus there is a the leaving group will leave with its pair of electron, and what it will form? And it will form RNu plus X minus. Okay, so what is happening here? Nu is been replaced by X. Okay, or X is been replaced by Nu, that is nucleophile. So this is a nucleophilic substitution reaction. So a replacement of one atom by another. Okay. So what is the answer? Anvita is saying it as D. What about others? Yes, D is the correct answer. Okay, D is the correct answer. It is, yes. Nagalambika also is saying it as D. Yes. So D is the correct answer. Okay. So yes. So it is D is the correct answer. Okay. So other options, if you see, they are okay. So C option, it is the addition reaction. C option is the addition reaction. Then here Rx plus H2. So this is also a electrophilic substitution reaction, just a electrophilic substitution reaction. Okay. Then here also what is happening here? Rx, 2Rx plus 2Na giving you 2NaX. So this is also just a substitution reaction, normal substitution reaction. Okay. So here what is happening? There is a nucleophilic substitution. Nucleophile has been replaced by another atom. Okay. So correct. D is the correct answer. So we'll go for the next one. How many stereoisomers does this molecules have? So this is the molecule CH3. Okay. CH3C double bond C. H. Okay. Then this is H. This is CH2 C H. Then comes Br and then CH3. So this molecule is been can be what? It can be having two forms. One is, this is trans form, and this is a chiral carbon, right? This is a chiral carbon. So the molecule is divided into two. It is divided as it is having a trans form and it is having a chiral carbon. So it is having a geometric center, right? This is called as geometric center. Trans means what? Same atoms across the double bond are at the same position, then they are called as cis. Okay, sorry, they are called as trans. When the same atoms are positioned at the opposite to each other, then they are called as trans. When they are placed okay, like this, if they are placed like this, then they are called as cis. They are called as cis. This is cis. Okay, what is trans? Trans is, so this is trans, right? This is trans, this is cis. So when the atoms are present, as similar atoms are present at the across each other double bond, then it is called as trans, and when it is at the similar side, then it is called as cis. Okay, so now here in this particular compound, the compound has been divided, okay, into two. That is, there is a stereo center also, and there is a chiral stereo center, as well as there is a, what you say, there is a this also, okay, stereo center as well as geometrical center is present, that is trans compound is also present. Now here, what, how many isomers it can form is, it can form trans, okay, it can form trans d d, then it can form trans l, then it can form cis d, and it can form cis l. Okay, so these are the forms. Okay, so these are the so this chiral carbon, it forms D and L. You know that chiral carbon, it will form D and L form, and this will form cis and trans. Geometric centers, they form cis and trans. So there are, how many stereoisomers can be formed? There are four. Okay, so trans D, trans L, cis D, and cis L. Because chiral carbon, they will show what they will show, this D and L forms, and this will show trans and cis form. So one with each, it will show four stereoisomer. I hope this is clear. Yes. So for today, this much is enough. The remaining questions we can solve in the next class. So if you have any doubts, you can ask me. Whatever has been taught for the class, is it clear? Yes. No doubts, right? Okay. Okay, then. Thank you, students. We'll end the session here. We'll meet in the next class. Okay.